Yeah, so hello everyone, and welcome to all of you on this afternoon. To this installment of the European Microwave Association's webinar series. And today I have here with me Alejandro Jiménez Sáez from Technical University of Darmstadt, who is giving a talk on Nematic liquid crystals for millimeter wave reconfigurable intelligent surfaces. So RIS is a topic. And today we're focusing on the hardware perspective of these devices, which are highly interesting nowadays. And maybe to talk a bit about Alejandro first, to welcome you as well. Thank you for joining us here and giving us some insights into this technology. So Alejandro received the master's degree in telecommunication engineering from the Polytechnical University of Valencia in Spain. And then he joined Technical University Darmstadt in 2017, where he got his electrical engineering degree. And in 2021, he received the German doctoring or the PhD degree with distinction in electrical engineering from Technical University Darmstadt, and the best dissertation thesis in electrical engineering award. After that, he obtained the Athene Young Investigator Award at Technical University Darmstadt, and now leads his own research group as an independent researcher entitled Smart RF Systems Based on Artificial and Functional Materials. And his current research interests include chipless RFID, electromagnetic bandgap structures, liquid crystal technology, and as today, reconfigurable intelligent surfaces. So highly welcome you, Alejandro, again. Before we jump into the topic, I'd like to take the chance to share some information about this webinar series, the European Microwave Association, with you. So you can find our YouTube channel using this QR code that we provide here, and you can also receive or view the other installments and the other events that we had in the series if you're interested in other talks as well. So join us there; it's highly interesting. And last but not least, I would just want to highlight to all of you that we are heading towards the 2024 European Microwave Week conference. So I highly welcome you to join us there in Paris this year in mid to end of September. And just to give you a short hint on this, so we're still in the early bird fee phase. So until next weekend, you have the chance to join us there at a reduced fee. Okay, and that's it from my side. I'll no longer take the stage here and hand over to Alejandro. Welcome.
Oh, thank you, Jan. Thank you for inviting me to be here today. It's really a pleasure to be allowed to present our work, our young work on reconfigurable intelligent surfaces. I'm just configuring the screen. I guess you can already see my screen.
Looks good to me.
Okay, so thank you also everyone for joining today. I'm glad to see also some well-known names in the participant list. So with no further delay, I would like to start with the topic of today. But first, let me introduce our research group at TU Darmstadt. So in case you don't know where Germany is, you can see it in this map. We are, so to say, in the center of Europe, close to Frankfurt in the case of TU Darmstadt. And we are a relatively big university, at least for German or for European standards, with over 24,000 students, more than 400 graduated PhD students each year, and over 300 professors, for example. And our electrical engineering department is also relatively long established here in Germany since 1882. Here you can see a nice picture of our former main building in the university in one of these sunny days that we don't have enough of in Germany. So now going to our research group, we are a relatively small and young independent research group at TU Darmstadt. Our name is Smart RF Systems Based on Artificial and Functional Materials. And we are investigating 3 different topics within our research. One of them is the realization of frequency-coded radar retroreflectors for identification, sensing, and ranging. We have also the topic of today, reconfigurable intelligent surfaces, for example, for 5G and 6G communications. And finally, reconfigurable RF components and antennas based on liquid crystal and electromagnetic bandgap structures for smart systems. As you already know, the topic of today is the reconfigurable intelligent surfaces for 5G and 6G. But I would also like to highlight here that obviously this whole work is not done by myself, or not alone by myself, but also by the PhD students, Jesus, Robin, and Mark, which are working on the 3 different topics. So the following slides are also work of Robin Noida, and I cannot highlight enough that it's not the work of a single person, although I'm the one that is allowed to present this today here. So let's go to the history of microwave liquid crystals. Maybe, or probably you have already heard the term of liquid crystal. And this was already a material discovered around 150 years ago on 1888 by Austrian botanist Friedrich Reinitzer and German physicist Otto Lehmann. And what they saw is that there was a group of materials that had some properties of a liquid, but also some properties of crystals, and they were happening simultaneously at the same time in the matter. So that's why they put the name of liquid crystals. Quite straightforward in this case. Although being discovered, the concept wasn't really followed for over 50 years. But then we can say that around the 60s, different research institutes, for example, RCA laboratories in the USA, started investigating into the commercialization of this material. Then around 30 years later, SAR Corporation was already demonstrating an active matrix, full color, full motion 40-inch display with thin film transistor array for the biasing of the liquid crystals. And with this, the topic or the concept of liquid crystal displays was established and came into the market. So 4 years later, we could already see laptops integrating these liquid crystal displays. And from then, most of us already know how it developed. And everybody has had at least 1 or 2 devices with liquid crystal displays by now. So it's quite a well-established concept in the optical domain for displays, and how they are manufactured. That's something that not everybody knows. How the manufacturers have decided or have developed over the years to fabricate these displays are by increasing the panel size in the fabrication process. So they started with around 30 times 30 centimeters panels, and they develop this process for larger and larger panels because they realize that the larger you do the panel, the more economical it becomes to fabricate these panels. And where we are now, it's at around 3 times 3 meters. So just to get an idea of how much it is, this is an 180 meters tall person next to one of these panels. So they are really, really huge panels where this, for example, televisions or monitors are patterned, and then after the whole process, the glass panels are cut in order to create our 65, 75 inches televisions that some people buy for home. And this is quite a current topic. We can see here that 3 years ago, still new plants were opening for the fabrication of so-called 10.5 generation LCD glass manufacturing, in this case in China. And here they say this is the most economical process to fabricate these large television displays. Why am I explaining this? Well, our idea is if we can fabricate large panels, large televisions in quite an economical process, and we can use liquid crystals for the realization of antennas, why don't we introduce the concept of liquid crystal reconfigurable intelligent surfaces for these large liquid crystal display manufacturing processes? And the idea is if we can fabricate antennas that are so large as 3 times 3 meters, for example, and also in glass, we can integrate them in the scenario here on the right. This is an outdoor scenario when we have a base station that is transmitting millimeter wave frequencies. So for example, 30 gigahertz, 60 gigahertz. And instead of isotropically transmitting everywhere, as we are used to from lower frequencies, these millimeter waves need to be focused on certain regions, because otherwise we don't have enough power to establish any communication at all. So the idea is that the base station doesn't need to have a line of sight directly to each user, but it can also transmit to some users by reflecting on the walls or on the windows of the different buildings. And then here we have reconfigurable surfaces that are able to steer how the reflection is happening on the building. So it doesn't need to be specular as a mirror, but it can be concentrated on single users, in this case on the street. Or we can also make these structures transmissive so that they receive some signals from the base station in the outside, and then they are able to focus them on single users inside a building. So this is the vision. This is not something that we have around and that this will take some years in order to be demonstrated, but we are on the way to it. And for this, I would like to define a little bit more in detail what is a reconfigurable intelligent surface. Here you can see a easier sketch of a base station trying to reach two users that are behind a wall. And the problem is when we are operating, especially at high frequencies, millimeter waves, maybe this is a term you have heard of, 30 gigahertz for the 5G band, or also 60 gigahertz or higher, then we cannot get through objects very efficiently. We lose too much signal power, so no signal is reaching actually the user. And then the idea is let's have some of these reconfigurable intelligent surfaces mounted on the walls so that they can receive the signal from the base station and they can concentrate it or focus it on the user. And very importantly, we can change the reflection of the reconfigurable, for the name, surface in order to serve different users over time. So what is an RIS, reconfigurable intelligent surface? On itself, it's just a large number of independently tunable radiating elements. So we have like pixels here in a screen that we can change the reflective phase, and therefore we can steer a reflection of an incoming signal. What is the purpose? Is to manipulate the reflection or even transmission in the side directions of focal spots of the incoming electromagnetic wave. What is the benefit of using it? Well, compared to relays, for example, the ones that you might have at home for Wi-Fi, that they just receive the signal and retransmit it. In this case, when we go to higher frequencies, it becomes more and more challenging to realize these relays in an efficient and in an economical manner. So by becoming completely passive and having no RF, no high frequency components operating at millimeter waves actively, then we can reduce the cost and the complexity. So these surfaces become increasingly interesting at higher frequencies. They cannot compete with existing technologies at 2 gigahertz, for example. And what do we need in order to realize these reconfigurable intelligent surfaces? Well, first, we need antennas that are able to operate at the desired frequencies, but we also need phase shifting mechanisms. So we need to have components that allow us to change the phase of each of these pixels independently. And this is actually the main part of our research, how to make these phase shifters and integrate them into reconfigurable intelligent surfaces. And this is what most of the presentation today will be about. So by the end of this presentation, I would like you to understand what you are seeing in this picture. So you are seeing two reconfigurable intelligent surfaces, one with 120 elements and another one with 750 elements. These elements or pixels are just these patch antennas, in case the name tells you something about it, that you can see here, and they are similar. They are just the same, but with different sizes. But first, before you understand what we are doing here, we need to start step by step, starting with Nematic liquid crystals, the material we use for reconfiguration. Then I will shortly introduce different reconfigurable components other than phase shifters that you can realize with liquid crystal. And then we will get deeper into the topic of the planar phase shifters based on liquid crystal display technology. And finally, I will also show some examples of the reconfigurable intelligent surfaces. So let's get into the topic, nematic liquid crystals. Why nematic, or what do we mean by nematic liquid crystals? Well, when we analyze the states of matter that we observe in liquid crystals, we can differentiate 3 of them shown in this graph. When we are very, very cold, when the material is very cold, we have a crystalline behavior, just a crystal, a solid crystal, as you can imagine, also for water, for example, when it becomes ice. On the right side, we have the isotropic state. just kind of a liquid when we have a very high temperature. But the special thing about liquid crystals compared to other materials is that they have this nematic state. And this is where we operate for the case of our antennas. So this is a state when the material itself, it behaves like a fluid, but we also see certain order, local order between one molecule and the next one. So they are not aligned in completely random directions here, but they are aligned almost in a crystalline direction, but that is moldable, that we can manipulate. So the interesting thing is also that this nematic phase is not very narrow in temperatures, but we can have it and we can observe it depending on the liquid crystal mixture between a large span of temperatures. In this case, for example, minus 20 degrees Celsius until 124 degrees Celsius. And this is the reason why our mobile phones or the displays in the car are able to operate and survive the different range of temperatures that we are using outdoors. So today, everything we will work on, I will explain in the rest of the presentation, will be concentrated on this nematic state of liquid crystal. So now what is so interesting about the liquid crystal molecule? Here we have a single molecule in order to understand. And what we have is an anisotropy. This means that depending on the direction of the molecules of liquid crystal, represented here by the vector n, and an incident RF field, in this case represented by the electric field, here in vertical, we have different permittivities. For example, when the molecule is orthogonal to the incident field, we have a low permittivity of 2.46 for the case of this liquid crystal mixture. And then, as we have different orientations of the liquid crystal, we have the opposite case on the right, where the molecule and the RF field are parallel to each other. And then we have a high permittivity of 3.53. Interesting of liquid crystal is not only these two extreme states, but the fact that by controlling the orientation of the molecule, we can generate any permittivity in between these two extremes. So we can have any permittivity between 2.46 and 3.53 in this case. So we have continuous phase shifts and not just switches. But this, despite being very interesting, is only useful if we have right ways of controlling the orientation of the molecules. So now we know that the molecules have this anisotropy, but how can we control the orientation of the molecules? This is something pretty flexible for liquid crystals. So we have different orientation or biasing mechanism. First is the magnetic biasing. It's quite intuitive. If we put two magnets and we have a magnetic field concentrated between these two magnets, in this case in the vertical direction, then the molecules will automatically align along the magnetic field. So therefore, if we start moving the magnets, then the molecules will also slowly follow the orientation of the magnets, and we will also generate, in this case, the horizontal orientation of the molecules. This is relatively difficult to integrate in many components because you need magnets and you need to move them, and that's quite a bulky approach. For this reason, people have come also with ideas how to bias these liquid crystals electrically. In this case, we have two electrodes, two metal plates, and we just generate a voltage difference, kind of a capacitor in between. And then we see also that the molecules align along this DC, this continuous electric field between the plates. Now, the interesting thing with electric biasing is that we don't necessarily need to move the electrodes, but we can just put two additional electrodes here. And then with a microcontroller or a microprocessor, we can change the voltages assigned to each of these electrodes. So we can generate states in between by just a programming code and not moving the electrodes themselves. So we can have something mechanically static that allows us to orient the molecules as we wish. So now what do we use in our reconfigurable intelligent surfaces? It's actually none of the completely or pure magnetic or electric biasing schemes, but we use a hybrid biasing scheme. On the one side, what we do is we have a substrate, we have just a material, a flat material, commonly glass, where we pattern in a plastic certain grooves that you can see here in light blue. So we have a material that we just scratch with a velvet cloth, and then we generate these small grooves. And very interestingly, the molecules of liquid crystal already align mechanically to these grooves. And we can therefore, when we apply this to a glass with this polyimide film or this plastic film with the grooves, we see that the molecules on the edge of these grooves already align, in this case, in the horizontal orientation. Now, interestingly, because we have a liquid crystal and not just a liquid, the molecules in between these two surfaces, top and bottom, they don't stay vertical, but they also align in a crystalline way. So slowly they align in the same direction as the neighboring cells. So with this, we can fix a certain orientation. Let's say if we don't do anything to the surface, the material, the liquid crystal between these two anchoring layers are called, it will orient directly horizontally. Now we need to control the orientation of these molecules. We need to be able to generate the vertical one. And for this, we add two electrodes, two metal plates to the surfaces of this glass, and we apply a voltage between them. And then we can counteract the anchoring forces, the mechanical forces, by these electric forces, and reorient the molecules in the vertical direction. Here you can see a little bit more descriptive view of this effect. So between applying no voltage to the two plates here in the top and the bottom, and having all the molecules represented here by cylinders in the horizontal direction, to applying a very high voltage and getting all the molecules in the vertical direction, we can have all the states in between just by controlling what the amplitude, the voltage of the voltage difference between the top and the bottom plate is. Having said that, we can see here two important parameters that we find when we start building these structures with two opposing electrical plates, and then here two glasses, and then a liquid crystal layer in between. So this you can imagine almost as your LCD display, liquid crystal display. You have two glass plates and you have some liquid crystal material in between. Now, if we don't apply any voltage between the plates, we have the horizontal direction for the liquid crystal molecules, and we have, in this case, a vertical direction for the electric field. So we have a low permittivity here on the left of the graph. When we apply a voltage, we rotate the molecules. And this is not something that happens in an instant, but it takes some time that can be modeled by this formula here that we won't go into detail today. Most interesting is when we remove the voltage between the high voltage and we just apply 0 volts again, then these molecules will slowly orient along the grooves of the alignment layers we have applied to the surfaces. And this is what we call the tau off or the switch off response time. Now, while tau on, how long the molecules orient vertically, we can control by applying higher or lower voltages, the response time. But for the off time, we cannot influence it by the voltage. We can just switch off the voltage, and we need to wait for the molecules to slowly reorient. Now, when we go to reconfigurable components, it's very important to get acceptable, like fast enough response time. So this tau off, which is the slowest one, should be as slow as possible. And for this, the only thing we can really influence is the selection of the liquid crystal mixture. This gives us some mechanical parameters here, like the elasticity of the liquid crystal molecules. But especially what we can design when we have a certain mixture we want to use is the structures to have a very low thickness of the liquid crystal layer. So intuitively, the closer we bring the two glass plates of the surface, the less amount, you can say even the less amount of molecules we have in the vertical direction. So the faster it will be the reorientation of all the molecules towards the horizontal direction. And just by modeling with this equation, by making some plots with this equation, you can see here the following curves, which just represent how different liquid crystal layer thicknesses from 0 to 100 micrometers, or here on the left from 0 to 5 micrometers, affect the response time. And this is a plot here for different liquid crystal mixtures. So it depends on which liquid crystal you are taking. There are different liquid crystal mixtures, and with them you can get different response times. But the behavior is clear. If you want to be below 1 second or 2 seconds of response time, so if you want to be relatively fast, at least for the human eye, then you need to go to liquid crystal thicknesses below 10 or below 5 micrometers. And this is the reason why we also target these 4 to 5 micrometers thicknesses in order to get sub-100 millisecond response times. So response time is a very important parameter, but there are other parameters that you should have a look at if you want to work with liquid crystals. The anisotropy we already mentioned. How much is the contrast between horizontal and vertical orientation of the liquid crystal molecule? Also the tunability, which is kind of a normalized anisotropy. We have the dielectric losses. Usually what we want here is the lowest, the better, at least for antenna applications. If you want to do absorbers, then you want the opposite. But usually this is a parameter that we want to have as low as possible. Also the temperature range of the liquid crystal. In case you are targeting certain applications, it's important to know that, especially in outdoor applications, that the temperatures you will have in our surface, for example, that they will be supported by the liquid crystal material. All these parameters are not independent of each other, and this is something we try to show with this three-dimensional graph. So on the x-axis, we have the tunability of the liquid crystal. This is a parameter that we want to be as high as possible so that we can, in the case of phase shifters, have the highest phase contrast possible, for example. On the vertical axis, we have the dielectric losses, and this we would like to have them as low as possible. So we would like to be somewhere in this corner of the graph. But we have a third dimension represented here by the colors, and this is how fast the phase shifters could be for us, or the liquid crystal components could be for a certain thickness of 4 micrometers. And what we can see is that there's a trade-off between these parameters. So as, for example, to simplify, as we reduce the dielectric losses of the liquid crystal, then we also get more viscous, so lower response times of the liquid crystal. So they become quite slow. So for fast applications, this is not the right mixture, but you would like to, for example, go to GT7 or GT8. All these numbers, all these names are products from the company Merck, which we collaborate with. They are the providers of the different liquid crystal mixtures optimized for antenna applications. So what you see is for applications where the response time matters, we usually tend to go to GT7 or also GT8 at the moment. Depending on the application, some of you might also be interested in using these liquid crystals at much higher frequencies than millimeter waves, so terahertz applications. And in this case, you can see results from a time domain spectroscopy measurement here at TU Darmstadt, where they saw that over this broad frequency range from 0.2, so 200 gigahertz, up to 1.6 terahertz, there are no surprises, let's say, or certain resonances in the behavior of the liquid crystal. So we have a pretty smooth behavior, and we can use this material at different frequencies. Also here on the right, the loss factor is relatively stable over the frequency range. So now that's everything about the material itself that I would like to present today, and we go now to different liquid crystal-based reconfigurable components. And for that, I would like to use this picture of an RF front-end, where we can see transmission and reception of a front-end, and how we have different components that we could be willing to do reconfigurable. We have on the one side, for example, the mixers. We have also tunable high power amplifiers, where we have to tune the matching networks and the input and output. We also have duplexers with switches and filters, and just filters and phase shifters, for example, here. So there are numerous components in an RF front end that we would like to do reconfigurable depending on the application. And a big disclaimer here, so we are concentrated on liquid crystals today, but this is not the only technology you can think about. I guess most of you have heard about at least one of these technologies, like semiconductors, ferroelectrics, ferrites, phase change materials, or RF MEMS, among others. So there are multiple technologies that are being investigated or even established already in the world of millimeter wave components, that all of them have their advantages and disadvantages. And today we are concentrating on liquid crystals. So let's see what we can do here for filters. In the case of filters with liquid crystal, we have 2 examples here that have been done in the group of Professor Rolf Jacobi here at TU Darmstadt. They are the pioneers in the work on liquid crystals for over 25 years. And here you can see 2 of the examples of components that they have demonstrated. On the left side, you have a filter for space applications, which is made out of a dielectric material here that you can see on the transparent gray color. And then there are small cavities of liquid crystal in the center here of the filter. And with this, you can create a reconfigurability in the filter response when you plug it into a certain system. On the right side, we have more actual design based on gap waveguide technology. In this case, we have a filter also, in this case with two outputs, 2 ports, input and output. And we have here 5 different cavities where we also have this small here plastic Rexolite containers having a little bit of liquid crystal in between. And with this, again, we can change the filter response by applying voltages, as you can see here. So this is the bottom part, the top part of the filter. And then when you close it, you can apply 2 magnets to force one of the orientations, and we can apply some voltages in order to force the perpendicular orientation. Further components, and the ones we concentrate mostly on, is smart antennas and phase shifters. And here you can see such an example. Also in the group of Professor Rolf Jacobi, we can see here an antenna which has a single input port, and it has here a power divider that goes from 1 to 16 outputs in a 4x4 matrix. So after the outputs, when you have here these dielectric waveguides on the top, in this case, it's not a reconfigurable component, but it's a high gain antenna that is transmitting only on broadside. But if you integrate here on the dielectric waveguide some liquid crystal that you can differentiate here by the yellowish color in the dielectric waveguide, then you can apply reconfigurability to the phase that it's transmitted, or that by the antenna, or it also works obviously in reception. The problem is when you do these 3D structures, you also need electrodes mostly in order to bias them, and you can see how then the component becomes a little bit more bulky or complicated. Obviously, this could be optimized further in order to make the biasing system much more integrated, but in this case is just a first demonstrator that was performed for research purposes here at the institute, and demonstrates we can steer the beam on this azimuth plane. Bigger demonstrator in this case for satellite applications, for a geostationary satellite, it's this horn antenna array that you can see. It's 8x8 horn antenna array here on the left, and then this is repeated in order to generate a 16x16 antenna array at the end. And what we have for the reconfigurable component that has LC in is this small stub here, which is placed on the waveguide before the horn antennas. And by creating here this plastic, also Rexolite container filled with liquid crystal in, and by biasing the orientation of the molecules of liquid crystal, we can also reconfigure the response of this horn antenna array. In this case, we just want small adaptations of the response of the array. We don't want large beam steering of them, because it's just in geostationary orbit, and we would like to just make small corrections. More planar solutions, closer to what we will be presenting today. It's this liquid crystal-based planar antennas done by the company Alcan Systems. And they have done these patch antenna arrays. You can maybe distinguish the patch antennas here. These are 8x8 modules that can be built next to each other. And there at the end, you have such a large antenna array for satellite communication, so for reception in the Earth of signals from the satellites. And this is built in liquid crystal technologies. This is one of the first prototypes where they integrate liquid crystal for the reconfiguration of the beam, so they can scan the sky in order to find the right satellite or to switch between satellites. Let's say a smaller version of such an antenna and integrated in glass. You can see it here. And in this case, it's for millimeter waves. It's for 30 gigahertz, 5G communications. This is an antenna that is able to establish a link with a base station outside, and is able to configure the beam in order to point towards the base station. And as you can see, liquid crystal, as it monitors, is on itself a transparent antenna, a transparent material. So if you also do the metallization of the structure, the electrodes, and so on, transparent, then you can actually also reach transparent antennas, as in this demonstration. So that's all for this introduction of liquid crystal as a material and for different components. In the following, let's get a little bit more into detail into what are we doing for the reconfigurable intelligent surfaces, namely these phase shifters here on the right. So here we have again the same slide as before. We want to reconfigure beams with reconfigurable intelligent surfaces in this sketch between two different users. And we have seen that what we need for that are antennas, and that's something we won't concentrate now, but we will concentrate on the phase shifting mechanism. How do we use liquid crystal in order to integrate these phase shifters in the reconfigurable intelligent surface? A reconfigurable intelligent surface is on itself very, very similar, if not the same, as a reconfigurable reflect array. And this is something that has been done for over 50 years already. So we can gain a lot of knowledge of reflect array, how people realize reflect arrays. And what you can see in literature is that there are two main approaches to the realization of reflect arrays, namely the resonant architecture here on the left, where you have antennas or you have cavities that resonate at a certain frequency. And then you have some material. It can be liquid crystal, but it can also be a pin diode, for example, that is able to shift to change the frequency response of the antenna. For example, by shifting the resonance frequency, we are able to generate different phases in the reflected wave. So we have a resonant cavity, a resonator acting as an antenna, and we change its response by the material. Another approach is the delay line architecture here on the right. In this case, we have an antenna here integrated here on the top layer, but we don't have any reconfigurable material, no pin diodes or no liquid crystal in the antenna itself. What we do is we couple the antenna to a phase shifter. So a transmission line, which only purpose is to generate phase or amplitude shifts. And here is where we integrate the liquid crystal material in our case, and therefore we change the properties of a delay line, so of a transmission line. And by that, by receiving and retransmitting these waves, then we generate a phase change in the reflected wave. So we decouple the antenna itself from the phase shifting. So what is the right way of doing reflect arrays? Well, it depends on your technology, on what you want to achieve with it. In our case, our approach is the delay line architecture. So this is how we concentrate on realizing these reconfigurable intelligent surfaces. And I hope I can convince you today about why this is a good option. When we try to realize this reconfigurable intelligent surfaces based on liquid crystal, we came up with a problem. And this is that for the antenna itself, we are using patch antennas and we have a ground plane, and we would like to have a thick substrate in order to have a wideband response of the antenna. The problem is for the phase shifting layer, we would like to have a very, very thin liquid crystal layer so that we can have, let's say, fast response times. And they depend on the thickness of the liquid crystal layer. So if we integrate the liquid crystal, the antenna on the liquid crystal, then we want to have a thick liquid crystal layer here on the left, but a thin liquid crystal on the right. And when we analyze what kind of thicknesses we would like to have, well, we would like to have a substrate for the antenna that it's around 300 micrometers for 60 gigahertz, while for the liquid crystal, we would like to be on the range of 4 to 5 micrometers. So one approach could be to find a trade-off in between these two values and give up, for example, a little bit of bandwidth in order to get faster response times. But what we see is that these two numbers are too far from each other to have results or trade-offs that are satisfying for us. So our approach is let's decouple the antenna from the phase shifter. We can have a thick glass material, a thick substrate for the antenna, and have therefore a wide bandwidth. And then we can have a very thin, as thin as we want, liquid crystal layer, so that we can have fast response times simultaneously. So we get kind of the best of both worlds. The challenge when doing delay line phase shifters with liquid crystal is that the low contrast of liquid crystal, this change of permittivity between 2.5 and 3.5, this is not much. This is a low 25 to 30% contrast, and this requires long transmission lines in order to generate a full phase shift of 360 degrees. But this is where we have developed our expertise. So this is our added value in the research that we have provided during the last years, is to realize these liquid crystal phase shifters compact enough. So we would like to be below 0.5, 0.45 wavelengths, so that we can put the antennas very close to each other, and therefore we can avoid having any grating lobes. In case you have seen antennas, you know a little bit about antenna theory. If you put the antennas farther away than 0.5 wavelengths, then you are kind of not respecting the Nyquist limit, and then you will have grating lobes. So you will be radiating power into the directions that you are not willing to. We also want to be wideband, so we would like to have bandwidths above 10%, and we want to have low losses. The losses, we measure it in dBs, and we are typically in the range of, let's say, 4 to 7 dBs for liquid crystal. So you don't get much better than 4 dBs because liquid crystal on itself has certain losses because of the same anisotropy that we use for reconfigurability. We would also like to be very fast, so below 100 milliseconds. And that's for liquid crystal material, this is quite a good response time that we can get. So let's see, how can we design these phase shifters, and why do we have this strange structure that you can see here in our phase shifters? Let's get more into detail here. What are the requirements that we would like to have for a phase shifter realized in liquid crystal? Where we would like to have low loss here. And the loss, we measure it by the figure of merit. That is, how much phase shift can we get for every dB of losses that we make. So the longer we make the phase shifters, for example, the larger the phase shift we can achieve, but also the larger the losses. So kind of a normalization or a figure of merit that we have in order to quantify this is this FOM. We also like the phase shifters to be compact so that we can integrate them in antenna arrays or in the configurable intelligent surfaces. And we would like to have full 360 degrees tunability inside the unit cell, because otherwise we cannot flexibly reconfigure the beam. The response time, mentioned several times already today, and it will come a few times more. We want it to be as low as possible, so we want to have a low liquid crystal thickness. And finally, the wide bandwidth. We would like to have a wide bandwidth without increased side lobes. So we would like to have quite a linear response of the phase shifters. Let's concentrate on the loss. Let's analyze a little bit more in detail what happens with the loss of transmission lines. In this case, let's start with a simple microstrip line. When we have a strip, in case you don't know this transmission line, we have a strip, and then we have a ground plane. So a plate, a metal plate, and an electromagnetic wave travels in between this strip and the ground plane. Now, when we analyze the losses of such a transmission line, especially the conductor losses, the losses due to metal, we see that they follow this formula that we can find in literature. We would like to have very thin liquid crystal thickness. And what we see in this formula is that we have here a resistivity that is dependent on the material. So we cannot maximize it much farther than using, for example, copper in practice for the realization of the phase shifters. Typically, we would also use gold, even if it's a worse material from the loss perspective, but it's quite more stable for its use together with liquid crystal. And we cannot play much with this numerator here, but we can play with the denominator. We have a wave impedance, and we have the width of the strip. So if we would like to reduce the losses, we would like to maximize this denominator. And that's what we plot here. We plot how the impedance of the transmission line behaves when we change the thickness, the width of the strip. And we see that it follows this relationship. More interesting is what happens with the product of both of them, the product of the impedance times the width of the strip. And we see that it gets higher and higher. This is something that we want as we increase the line width. But we get very low impedances. And second, what we see is as we reduce between the black, the red, and the blue curve, we are seeing that we are reducing the thickness of the liquid crystal. We have lower values. No matter what we do, we have lower values of this product of wave impedance times the width of the strip. So as we become fast, we also become very lossy. And this is not something that we want. So we want and we will reduce the thickness, but then we will lose this product of the characteristic impedance times the width, and then we will increase the losses. So we have increasing conductor losses with decreasing thickness. And this is something that is quite well known already, for example, for CMOS technology, where you have very thin substrate thicknesses and you have tremendously high losses for transmission lines. So you need to make them very, very short. So we analyzed this together with liquid crystal, and we saw, okay, what happens now if we add some defects into this transmission line? So we create this we remove the metal in this dumbbell-shaped form below the strip, and then we analyze what happens with the equivalent circuit of a transmission line. So by introducing these defects, what we have is that first, we affect the inductance of the transmission line because we are changing the paths that the currents need to follow around the dumbbell form. So we are increasing the path, we are increasing the inductance as well. So we are increasing the characteristic impedance. And now we can also say, okay, we have an increased characteristic impedance. Let's also increase the capacitance so that we have a relatively constant impedance. So we can increase the width of the strip in order to increase the capacitance, and we keep the same wave impedance or characteristic impedance. With this, what we are having is a wider strip with the same wave impedance. So we are actually maximizing this product. We are getting better values of this product, and we expect, if this formula still models properly the losses in such a transmission line, then we expect also the losses to be reduced. So we say, okay, this defective ground structure should reduce the conductor losses. But this is something you need to check from the model. You need to go to full wave simulations, and we need to check, is this really true? Does the formula still, and our intuitive understanding of this formula still accomplish in the real world? Well, we see in this case that yes, this is the case. So when we have a thick microstrip, here in this graph, you can see how over frequency, in this case, optimizing for the 5G millimeter wave band between 25 and 30 gigahertz, we have here the power lost for a phase shifter that allows us to make a full wave phase shift of 360 degrees. And we see when we have a thick microstrip, everything is good. We have certain losses around 6 dBs, but we still have some power that we get out of the phase shifter. But when we reduce, for the microstrip line, when we reduce the thickness to 4.6 micrometers, the microstrip becomes very, very lossy. So we lose 100% of the power almost. So we don't get any output power despite the proper phase shift in the phase shifter. Now, the interesting thing comes with the defective ground structure. When we apply these defects and we widen the strip, what we see is that we get, even for a very thin liquid crystal layer, we can a performance that it's even better than the 20 times thicker liquid crystal microstrip line. So therefore, we can affirm, okay, the defective ground structure allows us to reduce the thickness of the transmission line by a factor of more than 20, and therefore improve the response time when we analyze the response time by a factor of 20 times 20, 400. So this is a huge increase in the response time, improvement in the response time that we can get by using these defects and reducing the thickness. Here you can see separated the conductor losses in the metal from the dielectric loss. And what we see is that when we have a thin microstrip line, the conductor loss is very high and it dominates. Almost all the power is lost in the conductor. But when we apply our defects, then we get a much more balanced loss. They are lower first, and also they are much more balanced between conductor and dielectric. So we have losses both in the metal, but also in the liquid crystal itself. So that's the reason why we do this pattern that you have seen. That's the reason why we vote for the defective ground structure for the realization of the phase shifters. Now let's see here some characterization results, some measurement results of these phase shifters. What you see here is how we fabricate them. For the characterization with on-wafer, this is something you might be familiar with or not. We have two coaxial cables here, and then we have some probes here, which we can contact with our phase shifters, and we can have very accurate characterizations of the phase shifters alone without an antenna. Here you can see the materials. You can also find them in our papers, AF32 for the glass, GT7 for the liquid crystal, and gold for the metallization. And what you can see here is the results for simulation and measurement over frequency. And first, you have the figure of merit. We want to have a high figure of merit for low loss, and then on the bottom, the compactness. So we want to have a very low length of the phase shifters in order to have the full phase shift. So we want to be this line to be below 0.5 wavelengths here. And what we see is with the DGS-based phase shifters, we achieve both goals to have a high FOM, a low loss, and to have a compact phase shifter. Here you can see a summary of the results. The figure of merits are of over 70 degrees per dB of loss. We can have the phase shifters below 0.5 and response times below 100 milliseconds with a bandwidth of around 7 gigahertz in this case. For the phase shifters, we don't have an antenna yet. And this is what we will do in the last part of the presentation. Now let's put an antenna on the phase shifter that we have here. We have a DGS-based phase shifter. We have a slot here, and then we put an antenna on top of it. And the beauty of the configurable intelligent surfaces is as soon as we have a unit cell, we can just repeat it over a certain area, and then we directly have the reconfigurable intelligent surface. So the step between a unit cell and the whole surface is well, has some challenges, but it's pretty straightforward. An important thing is the fabrication, and I won't go into detail here, but you can check our publications. Also, you can ask if you want to know more about the fabrication. We start with glasses, and then in our laboratories here in our clean room, we are able to metallize and selectively pattern the different antennas, phase shifters. And then a very important thing is the liquid crystal. When does the liquid crystal come into the structure? This is the last step. So handling liquids is always a problem. It's always challenging, especially if you don't have experience on it and you are just an electrical engineer. So how this is done is first you have the whole structure mounted and assembled, and then in the last step you fill it with the liquid between these two plates. So it looks like this before being assembled. We have here in this case two reconfigurable intelligent surfaces. We have here the top plate and here the bottom plate. And we have, you can see here how the glass wafers look like, and then they are mounted to each other. And here is everything we have in a unit cell. This is the part that is repeated periodically over the whole surface. So we have a single unit cell with a phase shifter, an antenna, and then here on the left, you can see how we apply a voltage for the biasing of liquid crystal. So we have biasing electrodes on the sides of the surface, and then they bring the voltage, the low frequency voltage here, in order to the actual phase shifter transmission line here. So they apply a voltage to this metal strip in black. What we also need is that the RF wave doesn't couple into the biasing. So for that, we make lambda quarter transformers that you can see here. So how the biasing works, we already explained it at the beginning, but you can see here how it actually behaves. So just by applying a single voltage difference between the top and the bottom plate, here we can align the molecules selectively at any orientation. So what we can get is different phase shifts depending on the voltage. And what you can see here on the left is how the phase behaves over a frequency, and on the right, you can see how different voltages generate a different phase shift for the frequency of 60 gigahertz in this case. So what we see is that the dependency is not linear, but until 2 volts, for example, the molecules don't even move much because the mechanical forces are higher than the electrical ones. But then they start moving quite a lot, just with plus minus 3 volts here. This is volts peak to peak. So plus minus 3 volts are enough in order to use like 75% of the contrast of the liquid crystal. And then if you really want to get all the molecules oriented vertically, then you need to apply a slightly higher voltage, in this case of plus minus 10 volts. But we don't need very high voltages because we have very thin liquid crystal layers. So some people are used to working with voltages of 30, even 100 or 200 volts in order to orient liquid crystals. When you have a thick liquid crystal layer, we can operate with plus minus 3 or plus minus 10 volts. And here you can see the measurement setup. For the characterization of the liquid crystal reconfigurable intelligent surfaces, we have here one of our first designs mounted with a PCB for the controlling the different voltages applied to the phase shifters. And then what we have is 2 antennas here connected to a vector network analyzer. So one antenna is always at the same angle, in this case, normal incidence of the reconfigurable intelligent surface. And then another antenna is placed statically on the room. So when we rotate this, the RIS and the transmitting antenna in this case, then the receive antenna is changing the angle at which it is respect to the RIS. Here you can see it on the right with the azimuth. So we have incident wave that it's always normal. to the surface, and then we can control the reflected wave. That's the principle of using liquid crystal. We can apply different phase shifts to the different columns here. So you can apply different voltages here. The voltage is applied to all the elements in a column, and then these elements generate a certain phase shift of the wave that is incoming from the transmitter. So the black arrow here, it gets reflected into the different directions depending on the voltages we apply to the surface. So we demonstrate reconfigurability in this case plus 40 degrees. So incident angle 0 degrees, reflected angle 40 degrees, or reflected angle 20 degrees. And we also have -20 and +20 degrees. And what you see in these graphs is the angle on the x-axis, but you also see the frequency. This is not angle, this is frequency on the y-axis. So with this, we demonstrate, or we saw that this behavior is not completely narrow band. So we are not concentrated on a single frequency, but we are trying to get a certain bandwidth, for example, for communication purposes, or for getting operation with multiple carriers, for example, for the case of 5G millimeter waves. Here you can see a summary of how the reflection behaves. We are transmitting always from 0 degrees, and the reflection doesn't work for 0 degrees for the simple reason that the transmitting and receiving antennas are blocking to each other. So we can only get reflections on different angles other than 0. And we can see how it works at -20, -30, -40, and -50 degrees. When we get to -60, then the performance deteriorates already abruptly, as we expect from planar antenna arrays based on patch antennas. So here, a summary, we have the top view and the bottom view of the reconfigurable intelligent surface, this first demonstrator we did. And you can see here on the right the different patterns, also the angle versus frequency plots for the different angles. And here a summary table that you can find all these informations in our recent publication in the journal Nature Communications Engineering. And what I would like to highlight here is the 120 elements we have with the 0.45 spacing between elements. So the elements are closer than 0.5 wavelengths, and therefore we avoid any grating lobes in the reconfiguration patterns. We also have a response time, sub 100 milliseconds. This is quite a very, very good value, a standing value for the realization of liquid crystal planar antennas. And we have a bandwidth of over 10% already with this antenna, slot coupled antenna to the phase shifter. And this is thanks to the coupling to the thick glass substrate that we are able to use. Now, a very brief comparison to other works. Most other works, especially in liquid crystal, are based on the resonant architecture. So they are based on an antenna, on an antenna that it's whose resonance frequency is shifted by the liquid crystal material. And therefore, in order to get good performance, they tend to have relatively thick liquid crystal substrates. And even when they go thin, they stay over 10 micrometers thicknesses. In our case, we have 4.6 micrometers, and that allows us to, even having good performance in terms of bandwidth or loss, we have outstanding response times, especially tau off. This is the critical one of 70 or below 100 milliseconds. Most other works don't report these values, or they have values over a second when they have thicknesses over 100 micrometers. So for this reason, I hope you are convinced about the delay line architecture for the realization of liquid crystal reconfigurable intelligent surfaces. And here just a short demonstration or showing some of our recent results. We are now doing these reconfigurable intelligent surfaces larger and larger. You can see here one of them and how the reflection, the metallization is quite flat. So you can see really a mirrored reflection on the RIS. And here we can see a reconfiguration pattern where, compared to the previous one, we see that the patterns are much more clear, and the half power beam width is much lower because of the large size of the RIS. So let me get then to the conclusion of the talk. So what we have seen here today, we have explored the realization of these reconfigurable intelligent surfaces, our recent work based on liquid crystal. In the presentation, we have explored the basic physical principles and history of the nematic liquid crystals for both microwave and millimeter wave frequencies. I have introduced different liquid crystal-based reconfigurable components other than the LCD-based antennas. And then on the second part of the talk, we have concentrated on planar phase shifters based on this liquid crystal display technology, which allows us to create these large panels, large reconfigurable intelligent surfaces for the integration in indoor and outdoor environments. And furthermore, I have presented our current structures and also now some perspectives on the future developments. So the perspectives in research, we never know where we are. We will head at the end, but we have a vision, and we have this vision that we can realize these intelligent surfaces in very large panels, and we can really integrate them in glass, in windows, because of their potential also to be transparent, thanks to the use of liquid crystal material. So we envision such a millimeter wave wireless environment in which base stations are just transmitting the power directly to the users and not just isotropically everywhere. It's not only just increasing the size, which is more of a technological question, but it's also about improving the how we realize these reconfigurable intelligent surfaces. So some goals we obviously have is to improve the efficiency of these surfaces, the bandwidth, to achieve even faster response times, because depending on the application, 100 milliseconds can be still slow. We also want to go to higher frequencies and not just stay at 30 and 60 gigahertz. And especially the characterization of these surfaces is quite challenging, and therefore we are developing, and we are also thankful for collaborations into developing accurate characterization of these surfaces. There are a lot of degrees of freedom how to characterize the different angles and different configurations of the different elements in the RIS. So this is a topic on its own, how to do that properly. We are a relatively small but growing group, and we are specialized in liquid crystal, electromagnetic bandgap structures, even for the phase shifters in this case, and the chipless RFID and detector effectors. And I would like to thank also especially the 3 PhD students that are currently in my group, Jesus Sanchez Pastor, Robin Noeda, and Mark Speth, for their work, and all of you for attending. We are looking for collaborations, and yeah, thank you very much.
Yeah, thank you, Alejandro, for giving us insights into this very interesting technology and this work of yours and your group, of course. Yeah, so as you might have seen, there's an ask for, or you can ask questions now. Maybe we just have a look at 2 of those that were already written down some minutes ago. So I guess the second one is a bit philosophical. I'm not sure how much this can be discussed from a technical point of view, let's say, Alejandro. But maybe you have a hint on the usable bandwidth with respect to the size of the array.
Yeah, I cannot see the question. Here, Q&A. Okay. Is the usable bandwidth to the planar wave propagation across the array? So I mean, I don't know the planar wave propagation across the array. I mean, if you do the substrate thin enough, that you don't actually have this planar wave propagation. What you have is beam squinting for sure. I don't know if the question goes in that direction, but it's not what is mentioned. So I mean, you can do large antenna arrays because they have also already demonstrated for satellite communications. For example, in this company Alcan, they were already at, if I'm not wrong, 64 times 64 and time elements antenna arrays, and they work. So I mean, they would work. You have beam squinting, that's something you need to take care of, and then there are people working on the theory behind how to optimize the different phase shifters, not just for trying to concentrate a single frequency in a certain direction, but so that different parts of the surface work into slightly different directions. So at the end, you can compensate a little bit for beam squinting. You can never neglect it or get rid of it when you have a planar antenna array, but this is an ongoing topic.
Yeah, there's another question regarding the physical dimension of the elements and their spacing relative to the operating frequency. Is it a quarter wavelengths, for example? So I think I've seen 0.45 at one of your slides. Yeah, so the element spacing is below.
Yeah, exactly.
Right.
I mean, the problem with reconfigurable intelligent surfaces is if you don't do them big enough, let's say let's at least 15 times 15 or 20 times 20 elements, the least, you have not enough power usually at the receiver in a realistic scenario to get a high enough receive signal. So you need to do them big enough because of their passive nature. You need to be able to focus enough the power so that you can really get some performance out of them. Then when you do them big, if you don't respect the element spacing, you get these grating lobes. And at the end, what you are gaining by increasing the size, you are starting to lose by having beams in different directions. So you have multiple beams, not only where you want it, but also in other directions. So you are reducing the efficiency dramatically, actually. So you need to take care of this. And this is something we take care of. So we only realize the first RISs completely when we got the phase shifters short enough to be integrated within this boundary of 0.5 wavelengths. And that's something we respect, this boundary. Otherwise, it would be very inefficient to realize these surfaces.
So I've seen you align the elements not in a rectangular grid, but have a shift in every second line, or every second column. Doesn't depend. Is signal routing for the bias voltage is also a problem, or does it not interfere with the RF because it's done on a different layer?
I mean, it interferes. So I think maybe I have here one of these pictures, for example, this one. So we have the biasing. In our case, we just do it per columns or per rows in this case. So you need to bring it to the line, and we are in the same layer. Because of glass, it's not that easy. It's possible, but it's not that simple to change the layer to make bias through the glass. This is starting to be even commercially available slowly, but to get it very repeatedly over large surfaces. So what we do in our clean room is we do it on the same layer, and then obviously you need to respect some distance to your transmission line, otherwise you will couple too much power. And this is one of the limiting factors, but this is in reality, from a technological point of view, is not a limiting factor anymore, because we also have liquid crystal displays with the biasing already for all of the pixels and everything. And this is doable, especially when you start integrating active matrix, thin film transistor-based biasing schemes. This is something we don't approach in our clean room because we are just concentrating on let's do efficient phase shifters. But this is something, as soon as the market is there, the solution is already there as well.
Okay. And is there a coupling between adjacent delay lines, or so? At least if I have a look at your substrate, there's somehow no need for some isolating structures or something like that, right? So how strong is the coupling?
Yeah, so we simulate that. Measuring it that is difficult because of the passive nature. I mean, we could do just sample structures. What we do is in simulations, we see, for example, like the coupling is very, very slow, very, very low. The coupling comes actually through the antennas themselves on the other layer. The antennas are, like in any antenna array, they are coupled to each other. You have mutual coupling, but not through the phase shifters. What we do have is a weak, but still some radiation from the end of the phase shifters, because we are doing a reflection. It's an open end. So I would say this is more important than the coupling actually between the lines. It's still, we see that it's very, very, by doing it properly, it's very, very low, especially because you have such a thin liquid crystal layer. So it's a 5 micrometers thickness of the substrate. Thin substrates don't radiate much. Also the open end is quite efficient way of terminating the structure.
Yeah, and maybe just as an outlook, if you would like to scale this up to higher frequencies, what is your limiting factor? Is it the structure size that you need to realize, or are it the dielectric properties of the liquid crystals?
I mean, the structure as it is now, it's scalable. The problems, for example, the question about the wave propagation across the array, you will have it if you just keep the substrate, the glass thickness constant, which is sometimes something everybody would like to have, because if you want to fabricate them and you already have a process, you don't want to change the thickness of the glass, or it will become more flexible. So you will have to start from zero, getting the different processes working. So if you do a thick substrate for the glass, then you will be lost with the surface waves in the array. You need to make it thinner, and this is a technological difficulty to make the different process, for example, in the clean room, due to this thinner substrate you will need at higher frequencies. Also, every detail will become finer for the processing. So, for example, the gaps, these tumbles, they will become smaller and smaller, so they become challenging. But this is something solvable. The only problem is if you just scale everything and fabricate it, somehow you fabricate it, your losses increase a lot because you are getting much more, especially conductor losses at higher frequencies, lower conductivity, and higher surface roughness as well, or higher effect of surface roughness. So you need to come, at the end, you will need to come with better solutions if you want to keep the losses acceptable. So you will need to make improvements in the delay line structure. I saw how we approach them at 30 or 60 gigahertz, but we will need better ways of doing them if we want to make efficient, let's say, terahertz reconfigurable intelligent surfaces based on the delay line architecture.
Yeah. Thank you, Alejandro. Once again, I think there are no other questions up to now. So thanks all of you for joining us here, and yeah, we're looking forward to the next event. And thank you for today, Alejandro.
Yeah, thank you, Jan, for inviting me, and thank you everybody for attending.
Bye.
Bye.